All right, welcome to this video on the applications of the separation of variables. We're going to just be talking about how we can model a whole bunch of real life situations by describing them as differential equations where we have to use the separation of variable technique in order to actually evaluate them a little bit more. So let's start off with this first one. We have the law of exponential change. So it says the rate of change of a quantity is directly proportional to that quantity itself. The differential equation that describes this growth is dy over dx equals k times y, where k is some sort of growth constant. If it's positive, it would be a decay constant if it was negative. And y is the quantity itself. So let's just do this little exploration so that we can recognize what this type of differential equation will look like. So, I mean, we have a hint. They've told us it's the law of exponential change. So we're thinking it's a good possibility that maybe this will make an exponential equation. So let's start off by separating our variables. So I'm just going to rewrite it over here first. So we have dy over dx equals ky. I'm going to divide by y, and I will multiply by dx just like we were doing last class. I'm going to integrate both sides, so I'm taking the antiderivative here. The antiderivative of 1 over y is going to become ln, the absolute value of y. And then the antiderivative of a constant is just going to be that constant times x. And then we have plus c, where c is a different constant than k. I know it's a little weird, but we'll survive with that, I hope. So let's solve this for y equals. Remember, it's trapped in a log form, so we're going to switch to exponential. I'm going to just re-show us the little trick with c that we learned last class, just to make sure that we remember why it happens. So we would get kx plus c, and what we learned was that with the addition up there, we could rewrite this as e to the kx times e to the c, and this is just a constant, so we can just rewrite this as c times e to the kx plus c. And something that I haven't really been talking about when we did this is technically when we do this switch with this absolute value, there's really a little plus or minus right here, but that plus or minus is going to get absorbed by the c value. So that's why I haven't really been constantly showing us that it's there, because it's getting taken care of. And I just realized now that I've made a mistake because that stuff's not there. My bad. Okay, so just as a reminder to you, I've given you permission to go directly to this step. You do not need to show that. Okay, so here's our final form of this. The general solution to a dy over dx equals a constant times y is going to be y equals some initial value there times e to the kx, and that is an exponential equation. So that is why we have this law of exponential change. So we're describing the rate of change of an exponential, okay? And what we want to pay attention to is the way that this is worded right here. It's, the rate of change is directly proportional to the quantity itself. So when we see that, we instantly know that this is what we're going to be writing down. All right, so let's look at an example of this so that we can figure out what's going on. So it says, during the COVID outbreak, the number of people that are infected at any time increases at a rate proportional to the number of people that are infected at that time. That is describing exactly that situation. It is a rate proportional to the value itself. Okay? So we have a couple other bits of information here, right? It says, if 1,000 people are infected when the epidemic is first discovered, and then there are 1,200 people after 7 days, we want to try to find the solution for this differential equation that satisfies these conditions. So what we're going to do is start off with writing this rate of change. Okay, I'm going to use slightly different letters because we're talking about different things here. So I'm going to have the rate of change of the population of number of people, basically, who are infected over time. So I'm going to do dt, and that's going to be equal to, because of this, proportional to the number of people, I'm going to do kp. Okay, so that's the exact same thing that we have up above, just with different letters. So we'll just, treat this like a normal thing. We're going to separate the variables. So I'm going to end up with a 1 over p when I divide by p, dp. equals k times dt. And now I'm just going to integrate both sides. So I'll get a natural log of the absolute value of p equals k times t, because my variable is t this time, so not kx, kt, plus c. I will switch this. Okay, so it's going to become y equals, we'll just immediately go into our c e to the k t. All right, and now we're going to try to figure out what both c and k are so that we can write this solution that satisfies the initial conditions that were given to us. All right, so what I'm going to do is change colors, and we're going to have this if 1,000 people when we first there. So when t equals 0, we have 1,000 people. And then we're also going to have when t equals 7, there's 1,200 people. So we're going to be able to use these 2 points to help us find c and k. So let's start off with this point. So we have 1,000 people equals c e to the k times 0. So e to the 0 power is 1, so we have c is going to equal 1,000 people. We knew that already from pre-calc and algebra 2, that this c value is the initial value when we have exponential like this. But good for us to show it. And now what we'll do is use this point. So we'll have 1,200 equals, I'll replace the c value with that 1,000, e to the k times 7 this time. So I'm going to divide by 1,000, that will give me 1.2, and you'd have a calculator at this point. So we get 1.2 e to the 7k. We are stuck in exponential form, so we're going to switch to log form. So that will give me 7k equals ln of 1.2. And then I just divide by 7. So k is going to equal ln 1.2 divided by 7. If we didn't have a calculator, we would just leave it written this way. We're going to pretend like we have a calculator. We type this in, we're going to get 0.026. So I can rewrite, I kind of have poor board management here, but we have our p equals 1,000 e to the 0.026t. And that is going to be the solution to the differential equation that satisfies the given conditions. So that was our first application. Did we make it? Did we survive? I'm hoping we did. There's a place for you to ask questions on Schoology, so feel free to do that. Let's look at a variation on this one that you also learned in pre-calc and probably algebra 2. It's Newton's law of cooling. We have a different way of defining it, and what we're going to end up doing is creating the one that you used in pre-calc last year. So we have the rate at which an object's temperature is changing at any given time is roughly proportional to the difference between its temperature and the temperature of the surrounding medium. So that's what we have, current temperature and temperature of the surrounding medium. So that's just like, like what temperature your room is right now, okay? And this time they're specifically telling us that it's actually a negative proportion, okay? And I would give you this formula. So up here, I wouldn't give you it, you'd have to create it. If we're doing Newton's law of cooling, I would give you this one, okay? So let's just find the general solution to the differential equation that we have here, and we will try to figure this out. So there's some things that are a little tricky here, but I'm going to divide by this t minus ts. So I'll end up with a 1 over t minus ts, which is not standing for Taylor Swift, it's just temperature surrounding medium. We're going to do dt capital equals that negative k value, and I'm multiplying the lowercase dt to the other side. So the little t is time, the big T is temperature, okay? And this is like the room temperature. Room temp. Too many T's, I know, it's a little annoying, but let's integrate both sides. So as far as we're concerned, this Ts is a constant temperature. Okay, so like the temperature of your room right now is like 70 degrees. It's not changing. So our variable that we're integrating over is actually just T, and we're assuming Ts is actually a constant. So we're just going to end up with natural log of T minus that constant. So we did an example in class last where we did like a 1 over y minus 1, and we basically just traveled that 1 in there with us. So same exact thing. And over here we'll have a negative k t plus c. We'll do our little switcheroo. We could get us out of this log form. So we have t minus ts equals, we're going to immediately move that c to be in front, e to the negative kt. So let's use this now to figure out what's happening at t equals 0. So we're just going to figure something out, okay? So at t equals 0, okay, and remember this is just an exploration. This is not something that you have to do every time. We would give you more information on a test or a quiz, but what we would do is we would have this t value right here we're talking about at the temperature, or at the time of 0, is going to equal CE to the negative KT plus that TS. So I'm just, adding this to the other side. And I'm letting this t value equal 0. So when I do that, this t of 0 value is going to equal C, and then e to the 0 is going to be 1, plus this starting temperature right here. And if we solve for C by subtracting that TS back over and rewriting this T0 business in a little different, so T with a sub-0 minus TS, this gives us the equation that you were using in pre-calc last year. So what I am doing is rewriting this right now. So I have T minus TS equals this C value. I'm going to use this. So I'm going to put parentheses, the initial temperature minus your starting temperature, e to the negative KT, okay? Where T0 is your temp at time 0, and TS is your room temperature, just like up above. And this was Newton's law of cooling that you used in chapter 3 of pre-calc, and we would give you this equation every time, and this is where it comes from. So we were able to use calculus to prove where that Newton's law of cooling formula came from, which we weren't able to do last year in pre-calc. So that's kind of neat. So let's keep in mind that this is what the formula is, and for now let's just assume I'm going to give you the formula so you don't need to memorize it. We can change our mind before we have a quiz on this, but let's do an example where we have a specific setup going on here. All right, so we have a hard-boiled egg at 98 degrees Celsius is put in a pan under running water. That is 18 degrees Celsius. After 5 minutes, we find the egg's temperature to now be 38 degrees. So how much longer will it take for the egg to reach 20? So let's just assume we've done all of this background stuff, and we're going to start with this T minus TS equals T0 minus TS e to the negative KT formula. All right? And we have some things that they gave us. So they told us that the original temperature at time 0 is 98. They told us that the surrounding temperature of the water is 18. And then they also said that T after 5 minutes is 38. All right? So let's try to break this problem down. Step 1 is we want to find the K value. All right? So let's just use the information that we have to see if we can figure this out. And what I'm going to use is this T5 is going to equal 38. All right, so we have this T value we don't know right this millisecond. We'll just pretend, okay? Minus the surrounding is 18 equals the initial temperature was 98. The surrounding was 18. E to the negative KT. So now that I have this equation, now I'll use this point. I wanted to do that sub-step so that I didn't have to substitute too much in all at once. It might confuse you. So we got the T value is 38 minus 18. We have this 98 minus 18. You could totally rewrite this at this point. E to the negative K, and then I'm letting T equal 5 because I'm letting this value over here be 38. So this is really 20. This is really 80. So I'm going to divide the 80 to the other side. So 20 divided by 80 is going to be 1/4 equals e to the negative 5k. Do a little switcheroo here, switch ourselves from exponential to log form. That's going to give us ln of 1/4, and then k is just going to equal that ln of 1/4 divided by -5. And in our calculator, we'll figure out what that is as a decimal. It is 277, and then we will store it. So remember, you can store things by hitting second stow, or just stow, sorry, my bad, which is right above your on button in the calculator. There's the on button, and then there's one that says stow. So you just hit that, and then you'll just hit alpha, whatever letter you want it to be stored as. Okay, so I always store mine as the letter K because that's what it is, and I don't have to think about it as much. So now that we have K, what we're actually going to do is figure out what this question is actually asking, right? So it's saying how much longer will the egg take to reach 20 degrees? So when I take this starting equation, T minus 18 equals the 98 minus 18 e to the negative k, which we now know is actually this 0.277 t, let's plug in 20 because that's what we're trying to figure out now. So I'm going to do 20 minus 18 equals the 98 minus 18 e to the negative kt. So 20 minus 18 is 2. The 98 minus 18 was 80. So I have 2 over 80 equals e to the negative kt. Let's switch forms. So negative kt equals ln of 2 over 80. And yeah, I know that's 1 over 40, but whatever. Do t equals that ln of, here we'll do the 1 over 40 for you, minus k. And remember that we have this stored. So when we type this in the calculator, we can just do ln parentheses 1 over 40 close parentheses divided by negative alpha k, or whatever letter you did, and I got 13.3. So for us to actually answer this question now, we have from the start is what we just figured out. So that's 13.3 minutes. They asked us how much longer, so that means that we have to do from the 5-minute mark, okay? There would only be 8.3 minutes left. Whew. So that's a question straight from pre-calc, but it's derived from calculus actually. All right? Like the most fun you've ever had in math class, I can tell. You're like, you're having a blast. So we're going to do a couple more examples here. So we're going to do example 5, which has a giant A and a tinier B, and then we're going to do example 6, and then we're going to call it quits. Okay, so it's technically 2 examples, but they're kind of, they look like they have a lot of in-between steps going on based on the amount of space we have on the page. So here we go. Rate of change of the number of bears in a region is directly proportional to this 1200 minus b of t. So there's that key phrasing again. Directly proportional, so we're going to be able to write a similar equation. I have the change in bears over time is going to equal some constant times this value, 1200 minus b. Okay, that's the directly proportional is why I knew to put the k value, and then of, or to, the 1200 minus b. So let's separate our variables and see what we end up with. So I have a 1 over 1200 minus b equals, whoops, not equals yet. Let's undo those things. db equals k dt. And we're going to integrate. And I know last class I told you I wasn't going to give you one that used u on this side, but it's a little bit easier if we allow this one to equal u so we can figure out and make sure we don't mess up. Because when we take the derivative of this, it's going to equal a negative because it's a negative b, db. So when I substitute this stuff in, I really have an integral that's a negative 1 over u du. Okay, and that will equal our integral of k dt. So when I have this negative, you can move it to the other side, which we talked about, kind of leaving the negative always attached to the other side, not this side. But here's another way that we can handle it. The negative will just stay in front. So we'll end up with a negative ln of this absolute value of u equals our kt plus c. I'm going to resubstitute back in the 1200 minus b. And at the same time, I'm going to multiply everything by a negative. So it's going to move it from the left side to the right side. So I'll get a negative kt. And again, when we deal with a constant, if I just make it negative, it still is just a constant. So I'm going to ignore the fact that we multiply that by negative. We can technically do that with the k value as well. So we could run this whole thing through with now a positive k instead of a negative, but we typically don't do it. Just like over here, how the equation ends up with a negative k. We could technically just let k be positive in the formula, but for some strange reason, we always like to leave that one as negative. And I don't have a good reason for why we do that, so apologies. Let's do our flipperoo. So switching out of log form into exponential, and we'll move our c value over at the same time. So we get this, and I'm just going to solve for b. So the way I'm going to do it is I'm actually subtracting this to the other side and adding this to the other side. So I'll end up with a positive b equals 1200 minus ce to the negative kt. And now that we have this, let's actually try to figure out what's happening here. So there's a little bit more information that they gave us that I think I didn't bother reading, but it said when t equals 0, the population is 300. So now that we know that, we're going to be able to find what c equals. and my alarm is going off to remind me to film this video for you. So enjoy that little blooper that I'm not going to erase. So I got that point, 0, 300 times 0, population's 300. We got 300 equals 1200 minus c e to the negative k times 0, so just 0 up there. All right, so this is going to give me negative 900 equals negative c, so c is just going to equal 900. Now that we have that, let's change colors. Let's actually do what this problem asks for, which is right here, what is happening at t equals 4 and b equals 600. So I'm using the point 4, 600. And I have b equals 1200 minus the c value is really 900, e to the negative kt. Let's figure out what k is. So 600 equals 1200 minus 900. Pretty please do not try to combine those. They do not combine, okay, because this 900 is attached to the e-value with multiplication, and PEMDAS says that we can't do that. But I can subtract this 1200 to the other side, so 600 minus 1200 is a negative 600. And now I can divide this 900 to the other side. So a negative 600 divided by negative 900, that's positive 2/3, will equal an e to the negative 4k. We are stuck in exponential form, so let's switch to log form. So negative 4k equals a ln of 2/3. So k is going to equal ln 2/3 divided by negative 4, which is approximately 0.101. So when I go to write my final equation here, I'm just rewriting this b equation basically. So I have 1200 minus 900 e to the negative, because the formula has a negative there, 0.101 t. Now if we had let that k value just be positive k, not negative k, then when we did all of this process, this would have ended up just being a negative. So it still would have ended up happening anyway, but there we go. So that is the answer to that question. That is the particular equation when there are 4 years later 600 bears when we started off with 300, and we know that it's directly proportional to this 1200 minus b rate. Now it says, what is the maximum number of bears that can fit in this region? And it gave us a hint. It said, hey, let's just do the limit as t goes towards infinity and see what that is. So when they're asking for this maximum number, what we can do is just say, okay, let's figure out if we let t go on forever and ever and ever and ever and ever for this exponential, does it just keep going forever, or does it eventually kind of taper out like the logistic functions that you learned last year that kind of have a upper bound to them instead of the exponentials which just go up forever and ever? So let's do a limit. We have the limit as t is approaching infinity. And I know some of you are freaking out right now that we're doing limits, but that's okay. It's not that bad, especially when it's infinity. That's a relatively easy one for us to figure out, I think. Because remember the way that I liked to teach you was to just directly substitute in infinity and then evaluate what happens. So if I do this times infinity, what I really have going on here is e to a negative infinite power, okay? And that's really 1 over e to an infinite power. And when we have 1 over an infinitely large number, that's really just 0. So we have that this limit is actually going to be 1200 minus 900 times 0. So that means that the maximum number of bears is just going to be 1200, because 1200 minus 0 is 1200. So bears, 1200 bears. That's our max number of bears. Wasn't that bad, right? Maybe not the most fun thing you've ever done, but, you know, manageable. And this is this is an AP style question right here, all right? Same thing with the next one. Very much so AP style, where we have these A, B's, and C's that are going on here, but let's read what it says. We have the rate of change in a population of a group of foxes at a local national forest is proportional to the difference of the blah, 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 okay? The reason I said blah, 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 blah is that they just gave us the formula, but we have that same thing. The rate of change is proportional, all right? So that's super important. They said at time t equals 0, the number of foxes is first counted. There are 40 of them, and then they gave us this equation. So let's just simplify this equation first by distributing the 1/4 through. So 1/4 of 500 is 125. So this is really the equation that we have working with. I think this will just be potentially easier for us to work with, but maybe not at the same time. I don't know. You tell me what's easier to work with you. Literally in my answer key in the next step, I don't work with it and I work with the original one, so no idea why I'm doing any of the things I'm doing, but whatever. We're having fun. Let's read what A says. It says, write the equation of the tangent line at t equals 0 and determine if this is an overestimate or an underestimate of the amount of foxes. So we know that this overestimate and underestimate stuff, that's our second derivative. So we're going to have to do the second derivative in order for us to figure that stuff out. Because that's going to tell us whether we're concave up, which means that we're an underestimate, or concave down, which means we're an overestimate. So let's just focus on writing the equation of the tangent line at t equals 0. So at t equals 0, there were 40 foxes. Okay, that was given to us way up here. It said, hey, 40 foxes when we start. So let's just find the slope. So df over dt equals this, 125 minus 1/4 of 40. And I'm pretty sure that that's 115. And now we can just write the equation of a tangent line. So I have y minus 40. Oh, I should not use y. We're using the letter f here. What's wrong with me? F minus 40 equals our slope, which was 115, and then t minus 0, which we could 100% simplify that and make that look nicer, but let's just not bother, okay? Because we still have to do a whole nother half of this problem, which is we have to find this second derivative. Now, this is where this equation comes into play, because here's our first derivative, and it's equivalent to this. So let's do the derivative of that. The derivative of 125 is 0. The derivative of a negative 1/4 f is going to be a negative 1/4 df over dt, because we're doing it over time. And just so happens that we know what that is, right? It's literally written up there. So we can replace this with 125 minus 1/4 f if we want, or it might actually be easier for us to write it the other way, which was the negative 1/4 times the 1/4 500 minus f, because this way we can write it as a negative 1 over 16. 500 minus f, a little bit easier to work with. So let's think about what happens here, and I know I'm running out of room, I apologize, but let's do it at this 0, 40 point. We're going to have a negative 1 over 16, and then 500 minus 40. So that's a negative number, which means that we are concave down, which means that we are an overestimate. Now, I really want to emphasize that on the AP, you would actually need to write what I just verbalized out loud. You would have to say that this is a negative number, which means it's concave down, which means that it's an overestimate, and explain your thought. They wouldn't really like if you just immediately said, like, it's over, because they might think that you're just guessing, and they wouldn't give you full points. So we want to start getting into the habit of kind of writing our thought process for some of these open-ended questions. All right. Find the particular solution to determine the number of foxes at time t years here. All right, so let's use the equation that they gave us. So df over dt equals 1/4 500 minus f. We'll do our separation of variables. I'm going to divide everything by 500 minus f. So I'm going to have the 1 over 500 minus f df equals 1/4 dt. Let's integrate both sides. Man, I have just lied to you numerous times now, because I'm again going to allow you to equal this when I specifically told you I was not doing this. I'm just a blatant liar, apparently. Apologize profusely, but I think you might get into the hang of it that because it's a negative variable, that it's just going to be a negative of the value when we're doing this. So but maybe you won't recognize that, and maybe you'll just need to do this every time. So there's our negative ln, absolute value of u. I'm just going to immediately replace it to save myself a little bit of writing room, and not put a parenthesis there because it's an absolute value sign, equals our 1/4 t plus c. All right, let's move the negative sign over. So we have ln, absolute value, 500 minus f, equals a negative 1/4 t. Again, we're just going to do plus c, because if we have a negative constant, it's the same thing as just saying we're adding a constant. Like, it's the same thing because our constant could be a negative constant. So let's flip the forms around. So we're going to have 500 minus f equals our c e to the negative 1/4 t. All right, and if we just rewrite this as, I'm going to add the f and subtract the ce business, we will have a 500 minus ce to the negative 1/4 t. So let's use our information that was given to us to figure some of these things out. So we were given that at 0.40, that was a nice initial population for us. So we have 40 equals 500 minus c e to the 0 power. So that's going to give us c equals 500 minus 40 when we do our little flipperoo there, or 460. So our final little equation here is going to be f equals 500 minus 460 e to the negative 1/4 t. And that's our general, or our particular solution. Sorry, particular, not general, because we found c. And let's just see, oh, here we got that maximum one again. So we're just going to say that maximum is telling us to do the limit, as t is going on forever, of this function, so of 500 minus 460 e to the negative 1/4 t. So we'll do our same process here. I'm just going to direct substitute infinity and evaluate what happens when I have 1/4 of infinity. So 1/4 of infinity is still just going to be infinity, so this is still an e to the negative infinite power, which is a 1 over e to the infinite power, which is a 0. On the AP, you will not need to show all of those steps, but you should show that this just drops to 0. So we'll get 500 minus 460 times 0, which is just 500 foxes, is our max number of foxes. So I hope you were able to follow along with this video okay. I hope you realize that you can pause, rewind, and you could play it at like half speed. I hope you realize that you could play it at double speed if you are getting this stuff and wanted to go through a little bit quicker. And make sure you put any questions in the Schoology discussion there, because I will try to either look at them before class on Monday or answer them over the weekend. All right, bye friends. I'll see you on Monday.